Hi, everybody. Welcome back to the conference. We've got another exciting session lined up. I'm Robin Laney. I'm from the Open University in the United Kingdom. I'm chairing today from a small market town north of London called Leighton Buzzard. Don't forget that if you want to ask questions or make comments, then we've got the Slack channels, a Slack channel for each paper indeed. Okay, so let's get started. So our first talk is a paper by Shlomo Dubnov entitled Deep Music Information Dynamics. So I'll now hand over to Shlomo.
All right, thank you so much for the introduction. I'll move on quickly to share the slides, and we'll try kind of to go through the ideas of this presentation as the first paper in the session. Just a second, I think I'm not sharing the right screen. Yep. Seems something else here. Can everybody see the slides? Check this for some reason. Sorry about that. Can everybody see the presentation? I hope I'm sharing the correct slides.
Looks good to me.
Yeah, just making sure that I'm showing the slides.
Yeah, they look good to me. So I'm assuming they must be the same ones that other people are seeing.
Okay, great. So sorry about that. So the title of the paper is Deep Music Information Dynamics, and it's going to be somewhat of a conceptual presentation, and the whole paper is really trying to develop a method or a system for thinking about music as a combination of, I would say, somewhat cognitively and musicologically inspired ideas and tools, mathematical tools to try to kind of realize this into something that could be testable. And, you know, we'll be kind of going on the boundary between talking about concepts of music and the technology aspect of this, or mathematical aspect, which is a challenge that I often encounter, and I embrace it because you know, I'm sort of have these two hats. I'm in the music department, so actually even teaching a class on the information dynamics to composers and performers. So in this sense, the conceptual approach, the terminology, if it can inspire creation, that's one of the goals. On the other hand, you know, in CS, in data science, you actually want to have tools that you can test. So given that motivation, I would like kind of to move on to the plan of the talk. And as I said, since I'm going to talk about this in a very broad sense, I'll start with the concept of Bayesian brain, and which is kind of related to machine learning and representation learning. I'll talk about music information dynamics. I'll relate this to human cognitions through the concept of rate distortion, which is an information theoretical concept, which appears also in machine learning. And eventually I'll kind of hopefully synthesize everything into a musical experiment where the goal is to model musical surprise using this let's say new model. It's not a new model, but it kind of changes the music information dynamics to consider also questions of representation. So very briefly, Bayesian brain is you know, an idea that Helmholtz coined, where he assumes that our thinking process has this little man in the head that is entertaining hypotheses weighting evidence, making decisions, and basically doing inference. So there is this active thinking component or active statistical component for which, the Bayesian theorem is actually the basis of estimating some kind of a latent states. And there's this also aspect of active inference that suggests that the brain can select its own perceptions or act on the world so it maximizes evidence or minimizes surprise. Now, the part of the active inference is that the brain actually has control of what it wants to see, what it wants to hear. So it's not only the sensations that drive the brain drives its sensations. So as an example of Bayesian brain, visually, for instance, the notion that we see here, the Star of David, is actually our inference. I mean, there is nothing in the stimulus except for these lines and these kind of Pac-Man type of circles. But we complete this. So of course, you can say Gestalt psychology addresses these aspects, but we kind of aggregate, we do some processing on the stimuli. This one may be even more famous example. Once you kind of, if you're familiar with the image, you immediately see that there is a dog here, Dalmatian probably. But all we have here is basically a bunch of dots and blips. And the fact that we see an image is actually an inference process. So the question is, do we do the same thing in sound? So the overall concept, a little bit taking on ideas of Friston also, about the free energy in the brain. The kind of the concept overall is that there is the reality, there's some kind of underlying generative process that is driven by some hidden states, but all we see are the observations. And then the brain is a generative process that tries to imitate or basically simulate the dynamics of the reality in its own way. And since it's not able really to simulate or capture the true statistics, the world has its own, sensations, has states and observations. So the states generate the observations, but since the brain cannot do that, it estimates this with an approximate function, which is a Q of S. So you can learn something which is simpler, and in this case, Q of S would be a neural network that learns something, and it basically tries to estimate some states given the observations. And this formulation, which is basically a variational inference, has different ways of writing this down, and I'll come back to all of these equations. So the purpose here was kind of just to show the first time that the idea of energy and entropy is formulated through statistical representations where we have kind of an energy. The reference with energy is the surprise, the overall accuracy that you can estimate seeing the world, and the entropy is the entropy of the brain itself, the states of the brain. So by finding the simplest explanations, the least assuming model, the brain kind of compromises between performing an action, which is estimating the world, and maintaining its own states. So the motivation really is summarized by this kind of a logic that in order to remain alive, an organism has to maintain homeostasis with the environment. It avoids surprising states, and it does this by minimizing approximation to surprise, which is the free energy. So a different approach to this Bayesian brain is so-called predictive coding. Now, predictive coding, if we apply this to musical listening, actually claims that the listener actively tries to anticipate continuations of music. So this is also an active process. And by forming this prediction, the listener reduces uncertainty about the future. And all of this can be measured as an information rate or information transfer over time. And we have also heard in this conference some papers that spoke about validation, violations of expectations, and as a principle that you can actually design your musical piece with certain trajectory of surprise. Now, this formally can be measured by so-called mutual information between past and the future. So when we have a source that generates music and you have a receiver, who is the listener has the past in its mind, it's available to him, and he tries to reduce the uncertainty about the future by conditioning or seeing how much of the next musical phrase or next musical instance can be predicted by conditioning this on the past. So this is kind of the definition of information rate in mathematical terms. And this concept was explored by many people, many researchers. And so the term of musical information dynamics is kind of trying to use notions of information theory where you treat basically the future or the present and the future conditioned on the past. And there are several versions of this. There is predictive information rate. Marcus Pierce and also Samar Abdallah did a lot of work on these aspects. So we have now these two different approaches: free energy, we have predictive coding. Both are considered instances of Bayesian brain. The free energy deals with inference of latent states, basically representation, whose goal is to capture the essential information about the world, the hidden causes, while the predictive coding approach to Bayesian brain deals with prediction of the future sensation, and kind of the math seems incompatible. So one of the things that bothered me for a while was it seemed that they both talk about the same cognitive principle, but kind of they were written in different ways. And one of the questions was, can we reconcile the two approaches? So this is the model that is proposed or described in the paper. And I'll have to define here a little bit the terms so the discussion kind of makes sense, because I'm going to refer to them. So we assume that we have musical input, and the paper referred to this as a surface. In my case, the surface are MIDI notes. And this is a good occasion to also thank the reviewers for a very detailed review. And one of the aspects that I was asked was, well, can't we deal with audio? I mean, the definition of musical surface is very broad. I mean, I mostly think about this almost like in Schenkerian sense. Musical surface is the notes, and then maybe you can extract a more abstract representations. But of course, as a framework, I do not limit, at least conceptually, this to musical notation, and even the question of how to represent musical notation, and whether we use piano rolls or kind of MIDI representations, or maybe use signal representations of notated music, some of the talks we had before. These are all very valid questions. So how to extract even the representation itself is a question. But then we assume that there is some kind of encoding that relates to some internal mental representation. So this kind of a poor sketch of a brain. So the assumption here is that, as the music moves forward in time from X to Y, so there is this implicit arrow of time moving from X to Y, also our internal states move from Z to T. So each one is basically encoded as the sensation goes in, but there is also another process of some dynamics that we learn, which happens on the latent states. So somewhat reminiscent of, let's say, the hidden Markov models. But the idea is that we have these four variables that I want to incorporate together. So the model assumptions are that you have a latent representation Z inferred from the past. So this one is inferred from X. X is the past, Y is the next step, the future. So Z is inferred from the past. We want Z to be as compact as possible, which means that one way to write this in information theoretical term is that it minimizes the mutual information X and Z. This is kind of the least rate that goes from X to Z, subject to some distortion level dx of Z. Of course, once we reduce the rate, we have some sort of a penalty. So this is where the rate distortion will come in. And now, of course, Z also has another function, not only to compress while still maintaining some level of quality towards the original input signal, it also has to predict something about the future. So this is an additional constraint or factor that we have to bring into the equation, and that the Z has to make a prediction about Y. Z actually also has to predict Y. Now, this is kind of the core of this whole formulation. So what is the best prediction? Well, if Z can predict Y as well as X, if we had the full information X, that's the best we can do is actually use the full information of X to predict Y, but we actually can predict it using Z because we kind of don't perceive X. We keep our perception here. So this actually predicts Y, while the best would be if we had all X. So if we can minimize the KL distance, or statistical measure of distance between these two predictions, that will be the best thing we can do. Now, with some algebra and information theory kind of relations, you can show that this relation is equivalent to maximizing the mutual information between Z and Y, or minimizing the negative. So, and then I also introduced, according to this model, you can also say that the prediction of the future based on the past internal representation can be written as two factors. One is how well it predicts the next mental represented state, and an error function, or whatever the extra information that is written down here. So this leads us to this slightly maybe scary looking loss function or goal function, utility function, that this is what the system basically has to deal with. The brain has to try to optimize all of these measures when it tries to listen and learn music or perceive music. So again, we have this compression factor and this prediction factor that we try to combine together. And of course, there is some loss between the surface, the sensation, and the perception. So I can be using terms of sensation as X and Y, and maybe perception as Z and T. So Z is predicting T, and Z is also predicting Y. So how do we implement this, right? So the simplest kind of idea that is closest also to the free energy is using so-called variational autoencoder. So we basically encode the surface, or X, to the latent representation Z using variational autoencoder. So we'll train a variational autoencoder on the musical piece. Now, how do we control the distortion level? Well, one way is basically physically change the architecture of the VAE. The less units we use will be reducing the number of bits that we have in the latent states. Instead of that, since I kind of wanted to play with training once and then changing the amount of information in the latent states, I used the rate distortion theory to basically throw away some of the information there. Now, the prediction of the information dynamics in the latent states is estimated using a model that I've been working for many years, so-called variable Markov Oracle VMO. I'll talk a little bit later why I chose this model, but basically we need some predictor, some time series predictor, but this time series predictor is applied not to the signal, but to the latent states. And then the prediction quality of the future signal from the past, which is this Z to Y relation, Z to Y, is estimated using some mutual information estimator. In my case, I used a method called MIND, Mutual Information Neural Estimator. So the VAE basically has this idea of encoding, decoding. And if you look at the formulation of the loss functions, also called the evidence lower bound, you can actually formulate both in very similar ways. They're basically written as free energy. You have the entropy here, okay, and you have the minus energy. So LBO is just a minus of the free energy, but they're equivalent. So you maximize the LBO or minimize the free energy. So there's this process of encoding the data into latent fake or approximation Q, which then is compared to true latent variables of the world to generate new data. So you have the encoder and you have the decoder here. If we want to control something, if we want to control now the size of Q or the amount of information in Q, we can use so-called rate distortion. So what is rate distortion? Basically, it's the idea that if you transmit information over a channel, if you add noise, okay, you might request or require that there is some distortion level. I kind of mentioned this this concept before. So it's the least information between x and y here, given or subject to some distortion constraint. So the whole idea of yes, sorry, there was a question. So I'll kind of try to speed up a little bit. It is known, or at least there is an approach to studying human perception as rate distortion, and the whole idea of the magical number 7 by Miller and others claim that if you can create experiments where, let's say, this is the number of objects that the person has to remember in identification experiment, so the probability of error and the number of bits, the probability of him guessing them right, can be theoretically described as these curves. This is the limit, and these are the experimental values. So actually, people are not as efficient as the theoretical limit is. And of course, these are different experiments. The more complex the experiment, the farther people are from the optimal curve. So one of the motivations for putting everything together using this formulation is this image from a paper by Alex Alemi, that is called Fixing a Broken Elbow, where he shows that the evidence lower bound criteria is actually written as a rate distortion, where you can generalize a little bit the rate distortion curve by having different weights on the rate and the distortion. So our experiment that said we train a VAE, instead of training different models with different rate distortion ratios, we use one model, we use the beta location, and the idea is to see how well we can predict the next surface from the previous latent state. Somehow the assumption is that surprise of a listener depends both on predicting the sensation of the next musical surface and the surprise related to dynamics of his internal representations, of his musical perceptions. So this is where I kind of distinguish between sensations and perceptions. Overall idea of, sorry, something in the equations here jumped away. But what we do is we have the encoding, we have the decoding, and we reduce the rate here using so-called beta location. So just to give an idea of what it means, to demonstrate the relations between input and output. So I call the input as a query, or as the input, and the improvisation is basically reconstruction with a variation of the encoder. And to judge the relations, I basically play them together. Where the idea would be, we can notice if musically they make sense together. Of course, going through variational autoencoder is not going to reconstruct exactly. Maybe with the larger model, it would reconstruct exactly. This is already some kind of a loss of reconstruction. But if I do encoding, decoding at what I call a full rate, this is how it would sound. The input will be played on a marimba, and the output is a piano. And so let's listen to this. So I think the overall, the purpose of this demonstration to show that they kind of sound harmoniously together. Of course, the melodies are different, the rhythm is different, but they still play and they change the chords in a way that they harmonize. If I reduce the bit frame or the bit rate between the input and the output and I play them together, I think we evidently start hearing that something is missing. Okay, so given this notion of, we basically create a more compressed or rough representation of the internal state, we can also measure the prediction quality at different rates. So in the experiment, I had 500 latent states, and I tried to do different bitrate allocations. So the graphs in the paper, basically, these are the latent states. So given rate of 10, I basically choose only 10 latent states and encode them as a binary variable. In what follows, I mean, the next one, 50 states, we have 50 of the 500 variables binary, and with 10,000 bits, we basically allocate 20 bits per each of the latent states, and we can estimate using this mutual information to see that for low rates, we basically encode only about 3 bits. For higher rate, we encode 5 something bits, and so on. So there's this logical progression that the number of bits that we are able to predict from the surface, of course, increases as we increase the bit rate.
It times them up.
Okay, so thank you. So the music information dynamic is a method that we use to estimate the information rate over time. I will skip that. And this is actually our kind of overall result, the slide. Given a musical piece, and in this case is one of the preludes and fugues in well-tempered clavier, we can actually estimate the information rate at the full rate and the lower and lower rates. And we can see that there are jumps that the surface itself or the high rate representation gives. And as we reduce the rate, we kind of segment this, or we have surprise in slightly different locations, although the more salient structural elements seem to still be maintained when we go to rate of 50. When we drop to rate of 10, actually everything becomes predictable. So that's kind of the summary. The idea is to present a new model, where rate distortion formulation is a combination of inference and prediction, or the question of representation learning, and the dynamics of these latent states. And the surprise of a listener depends on predicting the sensation of the next musical surface, and the surprise related to the dynamics of his perception, which is that latent process that goes on. And this is kind of the summary of this whole idea in more of a graphical method. And yeah, I'll
Thanks very much, Shlomo. Thanks very much indeed. It's a very interesting presentation. A lot to think about there. I don't think we've got any questions on the Slack yet, but there's still a little bit of time if people want to put some questions in. I'd just like to ask a question. Is it possible to empirically validate this some way with listener studies?
So I think the initial information dynamics studies, there have been a lot of work done with subjects. The very early work that we did was trying to estimate emotional force in a piece by Roger Reynolds. So there was an orchestral piece, and people were basically moving a slider to judge if they have emotional force or familiarity with the piece. So you have to go through somehow of that conceptual gap when you ask the people to report something and you measure something else, but you think that this is what the machine measures.
Yeah.
And Marcus Pierce did a lot of work with music information dynamics with listeners, and as I mentioned, Samar Abdallah has one of the early papers where he analyzes I think it was Philip Glass piece,
Yeah.
and he asked an expert musician to see if peaks in information rate actually correspond to what an expert musician
Okay.
judge. So this is kind of a, I don't want to call it anecdotal because it's not anecdotal, but you kind of have to invest a lot of effort of kind of
Sure.
matching what you think the user say and what the machine says. So
Okay. Thanks. We've got a question in now, so we've got a couple of
mm.
minutes left. This is from Gabrielle. How could you include in your model the many different contexts that affect our perception of music? For example, the physical context, room, situation, company, and our memories of the piece, which may affect our expectations about it. Do you think this is important at all to modern musical surprise?
It's an excellent question. So um, schematic expectation, rhythmical expectations. Do you memorize even inside the music? How do we extract information about harmony, rhythm, melody? There are tons of parameters. So this is why I said it's a very kind of broad conceptual representation. And I think one of the issues is that if you do have some sort of a machine learning that encodes stuff, you want to be able to maybe disentangle and look which part of that representation is working. So the rate distortion trick, in some sense, looks for more important latent variables, but we don't know what they are. And then the whole idea of your cultural training, that's even another dimension. So combine everything, the past, the knowledge of musical rules and progressions, and disentangling the musical surface. uh, I don't think there is one good way to do this. We see a lot of architecture; each one tries to do something else. So this is really, that's why I said it's more of that conceptual approach that we want to study the dynamics of some internal representation and the way it actually can regenerate, and they're both like factors. But yeah, I mean,
Okay. Okay,
it's
thanks.
exactly to the point. The question.
Okay, thank you very much. Now, there's a question from Roger, which looks a really great question, but we're running a bit behind. So, and I think this question might actually benefit from a online discussion in the chat. So if it's okay with you, and
Okay.
Roger, let's take that one offline because it's a really great question, but it just isn't time. Thank you very much indeed. Really,
Thank you.
really enjoyed the paper. Thank you.
Appreciate it. Thank you.
The next paper is from Shuki Da, Hun Sang, and Roger Dannenberg. And the title is Automatic Detection of Hierarchical Structure and Influence of Structure on Melody, Harmony, and Rhythm in Popular Music. I think we're taking this as a recording.
Hi everyone, I'm Shruti from Carnegie Mellon University, and I'm so glad to introduce our paper, Automatic Analysis and Influence of Hierarchical Structure on Melody, Rhythm, and in Popular Music. As we all know, structure is one of the most important elements in music, ranging from low-level melody and rhythm motifs to higher-level phrases and sections. Especially in recent music generation and evaluation tasks. How is music influenced by different levels of structure? And how do we determine the hierarchical music structure? These two problems became more and more critical in today's AI music creativity. Although there is a great deal of work relating to music structure, and we reference some of them in the paper. However, these two problems are still not well formalized. For example, there are many structure segmentation and analysis papers, but seldom do they study how music is influenced or structure hierarchy. Therefore, the goal of our paper is to tackle these two problems using the data-driven approach. Let's look at the first problem. We found two levels of structure in our analysis of popular music, composed of sections and phrases. For example, in this song, there might be multiple repetition phrases, like AABBB here, and each phrase usually contains 4 to 16 bars. And by combining those phrases, we can have bigger sections that forms the whole song. For example, in this song, there is an intro, a verse, a transition followed by a chorus, and the outro structure. So the question is, do these two levels of structure really exist? Are they just larger groupings? We hypothesize that there are different systematic effects of different structure levels that are visible through melody, rhythm, and harmony. If the hypothesis is true, then these two levels really exist and are important for music composition and perception. We test this hierarchy on a pop song dataset that contains 909 Chinese pop songs in MIDI. Notice that these MIDI files have separated melody and accompaniment tracks. We first determine the two-level hierarchical structure through an algorithm purely based on repetition and similarity detection, which we will talk about it later. And then we analyze the structural influence. Now let's look at some data. First, this is a figure showing how harmony interplays with different levels of structure in major mode. This figure has two axes. Vertical axis represents probabilities, but the horizontal axis is not time. It represents different locations in a song. For example, background means all the locations, no specifications. And next is a start location of a phrase, start location of a section, and so on. Here, different colors are different chords. Now let's assume if structure has nothing to do with harmony distribution, then all of the lines will be flat. No difference, right? And if there is only one level of structure, say we only had the big section structure, then the smaller phrase start, phrase middle, and end locations will be all the same, that's similar to the background. But it's not. Similarly, if the only structure was the smaller phrases, then when you get to the end of a section, that would be the same as the end of a phrase. But that doesn't hold either. For example, 5 chords, which is a purple line, are more likely to see at the phrase end within a section, but not at the real end of a section. Next, let's look at melody pitch scale degrees instead of harmony. Since melodic pitches are strongly influenced by chords, we would immediately expect to see that melody depends on structure. So here, we count only melody over tonic chords. Similar to previous harmony figure, if pitch distribution is independent of structure, all lines should be flat. And if we only have one level of structure, there shouldn't be difference between phrase and section locations. For example, we can see that scale degree 1 in melody, the blue line, tends to occur at the end of sections, but not at the start or middle of phrases. Similar things happen with rhythm, chord transitions, and other music elements, and you can read more details in our paper. Okay, so far, from the data analysis, we observe that there are at least 2 levels of hierarchy, and we discovered 2 of them, phrases and sections. And also, we see systematic influences by 2 levels of structure on melody, harmony, and rhythm. Here are more facts about our structures. For over 90% of the songs, 50 to 95% of their phrases are melodic phrases, which contains clear vocal line melody. And most of them are 4 bars or 8 bars long. There are typically 2 or 3 sections in a song, 3 or 4 phrases in each section, 1 to 3 distinct melodic phrases in each section. And data further shows that 20% of the sections are exact repetitions of the previous section in terms of phrases. For example, the first section is AB and the next one is also in the form of AB. While 29% of the successive sections repeat a suffix of the previous section. For example, AAB and the next section is AB. And 18% repeat a prefix. After studying the influence, let's look at how do we determine the hierarchical music structure. We propose a novel algorithm purely based on repetition and similarity. Imagine if the structure is unique, then all the making sense anymore. Thus, it is critical that we do not encode any domain knowledge in the structure segmentation, only depend on repetition and similarity. Here comes the framework of our structure analysis algorithm. First, we did some pre-processing steps of the MIDI. We extract the chord labels from MIDI and quantize them into beats, and also quantize the melody to 16th notes. And then we design a bunch of similarity metrics to detect repetitions, and use a novel A-star heuristic search algorithm with dynamic programming to come out with a phrase-level segmentation. In the last step, we propose some simple rule-based methods to further analyze the section from phrase-level results. Next, we will briefly introduce the representation of the structure hierarchy. How can we evaluate the structure, design of similarity metrics, algorithm procedure, and experiment results. This is a representation of our two-level structure. Each letter represents a phrase, followed by a number indicates the phrase length. Same letter means repetition. Uppercase letters are melodic phrases that has clear vocal line melody, while lowercase means non-melodic phrases, usually intro or transitions. Notice here group of bold phrases separated by empty space is section. Furthermore, for non-repeated measures, we use letter X to represent them. Next problem is how do we evaluate a phrase level structure? Is it the optimal or not? There is much ambiguity here. For example, suppose we want to analyze sequence of 8 measures. Use U and V to represent these measures, and we can describe the repetition as A4A4, where A is UUVV, or A2B2, A2B2, where A is UU, B is VV. Or we can even do A8, where A is the entire piece. But some descriptions are simpler than others. If we just count characters, we can see the first description is the shortest. So we formalize this idea as the structure description length, which is a weighted sum of number of segments and how much it takes to describe each segment. We believe that the structure with the lowest SDL is the most reasonable one. We look at every possible structure segment and pick up the one with the lowest SDL. Thus, we need a way to determine whether two segments are actually repetitions. This is how we calculate similarity between two sequences of measures. We form a weighted sum of these 3 different attributes. They are melody contour similarity using dynamic time warping algorithm, chord tone similarity matrix, and rhythm onset similarity comparison. And if the weighted sum exceeds the threshold, We then consider the two segments as a repetition. Detailed algorithm steps are designed as follows. We first find all repetition phrase pairs using the similarity matrix on previous slides. For example, segment from measure 1 to 4 is a repetition of measure 5 to 8. Then we merge these repetition pairs into sets that contain multiple repetition phrases. For example, here, these 3 repeated phrases form a repetition set. Next, we find the best combination of repetition sets that achieve the lowest SDL score using A-star search in dynamic programming. We further adjust the phrase boundaries. For example, 4 measures of phrase A followed by 1 extra measure can be merged into 5 measures of A if passing the similarity threshold. Finally, we use the non-melodic phrases and remaining non-repeated measures to detect section boundaries. Further optimizations and approximations are also possible. You can see details in our paper and appendix. Experiment results show that our full algorithm achieves 92% accuracy compared to human label, and its average runtime on a personal laptop is only 21 seconds for 80% of the songs. In conclusion, we propose a novel algorithm to extract both phrase and section levels from MIDI dataset based on repetition and similarity. And we also discovered that melody, harmony, and rhythm are all organized to reflect different levels of hierarchy. In the future, we hope to explore lower level motifs and patterns rather than just higher level repetitions. We can use this work to generate more coherent music, especially pop music, and evaluate music structure in AI music generation. Also, since results of this work are closely tied to established music theory, it offers a data-driven approach to study topics in music theory, such as chord function and melody. Thank you so much for your listening. Any questions or comments? Thank you so much for your listening. Any questions or comments?
Okay, thanks very much. That was great. I think there's nothing on Slack just yet, but I've got some questions.
Mm-hmm.
Yeah, so I've got some questions. Okay, thanks very much. That was great. So I've got a little bit of an echo. There's nothing on Slack just yet, but I've got some questions. When you were comparing with the human annotations, okay, thanks very much. That was great. When you were comparing with the human annotations, was there any interpretation required?
Actually, here I just directly compare if they are exactly the same. So, yeah. So some of the results might be correct. Might have a different annotation, but it's also correct. So in that case, I just count our result as wrong. So just direct comparison. Yeah, exact comparison. In that case, I just count.
Sorry, I'm juggling so many windows. Can you still hear me?
Yeah.
Oh, great. Sorry, I've got a bit of a muddle. I've got so many things going on. Okay. Yeah, so that's great. Were there any cases where what you found contradicted music theory? I mean, it seemed to me that most of what you found was fairly consistent with what music theory might say.
Yeah, actually we find some, but we haven't put in, because of the page length, we didn't put into that paper. Actually, it's interesting, we found that in the harmonic functionality, we found something called substitutional relation. For example, because you can see we have so many like repetition phrases. Like there are many cases that like two phrase, for example, two phrase A, they have exact like chord progressions. Only like in certain positions they change it. For example, they use a two chord in the first time in the first phrase A, and then they use like a four chord instead of a two chord in the second phrase. And we find that actually in that substitutional relation, there are many times people use three chord to substitute five chord, which is not out of my knowledge in a music theory. So actually that's kind of interesting. And I'm discussing that with my harmony teacher, and maybe you can see that in our next paper.
That's great.
Yeah.
Thank you. So there's a question from Rue. Does the POP 909 dataset have labels?
Yeah, actually, the original data set, they do not have the segmentation labels. So I manually label all the 900 songs. Yeah, so that's in our new repo. And the code is not uploaded yet, but the data is already there. We will like trying to fix it like as soon as possible. Yeah.
Okay. One more question from Jacopo. How did you take into account the subjectivity of structural annotations?
Yeah, because yeah, that's a good question. Actually, because I designed the algorithm and I annotate the data set. So actually, the parameters, how I tuning in our model is kind of like it's like okay with my annotation, but if like someone else annotated, there might be a problem. So actually in the future work, we can further customize the parameter tuning, maybe according to a few examples by the annotator, and to capture their personal like subjectivity of structure annotation. Yeah, that can be included in the future work. Yeah.
Okay, that's great. Thanks very much. There's some other great questions on the chat, and I think it might be good to take that offline. I think they might be better discussed offline and just in view of the time as well. But thank you very much indeed. That's very interesting. Thank you.
Thank you.
So the next paper is by Brendan O'Connor, Simon Dixon, and George Fasakis. The title is An Exploratory Study on Perceptual Spaces of the Singing Voice. So Brendan, are you ready?
I'm good to go, yeah.
Brilliant.
Great, let's... Okay. Hey, my name is Brendan, and I'm going to present my research titled An Exploratory Study on Perceptual Spaces of the Singing Voice. My research was supervised by Simon Dixon and George Fasakis and was conducted at the Centre for Digital Music at Queen Mary University of London. So a little bit of background motivation for why I wanted to do the study. I come from a background of electronic music composition myself, and I was quite interested in using the voice a lot more for its timbral aspects, more so than its narrative element in music. And the amount of variance in the voice and the different characters it can produce is quite fascinating to me, and it begs the question: how do humans hear different characteristics of the voice? And there is quite a bit of inconsistency regarding the terminology to describe perception and production of the voice between different voice specialists. And this could be because they're taking at different angles, whether they're performers or artists or scientists, analysts of audio. But I think something that would be great to have is a wholesome timbral space that clearly shows the closeness and the distances between different singing styles, which is what we're interested in. And if we're thinking about timbral spaces, then another interesting question is what are the factors that influence the timbral space of a singing voice? Is it the gender of the singer? Is it high registers or low registers in singing? Or is it the singer identity that causes timbral space to morph significantly? And we can also ask this question from the other perspective of the listener. what is it about the listener that causes them to perceive the voice differently? Does musical background have a very heavy influence? The answers to this aren't quite fully answered in the literature, but it's something we hope to explore. And especially, I'm quite interested in singing synthesis, which is what I hope to do next as a response to the next experiment. But we can use these timbral maps as a source of regularization and encourage our neural networks to learn representations of the voice that are similar to human perception. So, and this is how we went about doing the experiment. Basically, we in the study we wanted to generate timbral spaces, generate timbral maps, and analyze the relationship between different singing techniques. And we can do this using information given to us by the human participants that describe how similar or different singing techniques are from one another. What I'm basically describing is pairwise dissimilarity ratings, and that's when a listener will listen to two singing techniques and try to rate the similarity or dissimilarity between them based on timbre. And we compile these into, we get 120 of these dissimilarity ratings and compile them into dissimilarity matrices, which can then be subjected to clustering techniques, so we can develop an understanding for the relationship between the different styles or techniques of singing. And we can also use multidimensional scaling on this to develop a 2D or 3D representation that can show us a global general topology of how the different classes cluster together, or maybe they don't. That's another open question as well. So the data set that we used as the stimuli for this study was a vocal set, which has multiple singers all singing a variety of different musical exercises. And they do this using different singing techniques and utterances as well. So that's quite suitable for this work. And this is how we sample it. This is the hierarchy that we use. We randomly choose 3 male and 3 female singers from the data set. And for each singer, we generate a low pitched set or a low register set and a high register set. And for each set, then we extract 5 classes of singing techniques, which are straight, belt, breathy, fry, and vibrato. And again, for each class, we extract 3 examples. That gives us 15 examples in total for each set that we use. And this is basically what the instruction was to participants. Your task is to rate how similar or different the singer's sustained vocalizations sound to you due to different singing techniques. The challenge, therefore, is to rate vocal similarities irrespective of the singer's changes in pitch and utterance between recordings. And here we have a small snapshot of the interface that was given to participants. They have a reference button at the top, which gives them the reference audio. And then they have 8 comparative audio clips underneath that they can play, and then rate the dissimilarity between each of those clips and the reference audio clip on a continuous scale. Perceptual data clustering. So we basically have the perceptual data, and we want to try and determine what are the ideal number of clusters that represent that data, what's a good fit for it. So there's 2 options. There's 2 ways to do that. One is using the elbow of sum of squared errors, which reflects the within cluster variance, so how compact or how diluted those clusters are. And when we compare these SSE losses against the candidate amount of clusters, K, we choose the elbow point in the graph, which, as we can see here, is roughly around 2 or 3, but it's a bit ambiguous there, which elbow point is ideal. And if we look over here, we have a different example where there's no elbow point whatsoever in the graph. And unfortunately, this was quite prevalent in a lot of the participants' data. So it wasn't an exact science to get the optimal K value from the SSEs. So we looked at silhouette scores as well, which it represents the separation of clusters within the perceptual data. And if we look down here, we can see that the value of 2 clusters seem to be the optimal choice for the majority of data. And so we're going to use both 2-clustered analysis and 5-cluster analysis in the upcoming slides. 5-cluster analysis because of the amount of classes that we that are in the ground truth labels. Cluster metrics between conditions. So we compared several clustering metrics of the participants' perceptual data between the 3 conditions of gender, register, and singer identity. We compared the solutions for the optimal for the optimal value of k equals 2, as well as the ground truth number of labels for k equals 5, and performed Mann-Whitney U tests with respect to the clustering metrics of SSEs, silhouette, and accuracy. In this case, accuracy compares the combination of cluster assignments from the perceptual data against the ground truth class labels. And if we look at this table just below, we have the k values on the left, the metric that we're measuring for each comparison. And in this left column here, we have all the conditions that led to a higher accuracy versus the conditions that led to a lower accuracy. So looking at this table, we can see that the male 2 produced very low accuracy scores compared to the majority of the other singers. And it's also prevalent in the clustering for clusters of the metrics for k equals 5 as well. And conversely, we can see that female 5 has a much higher accuracy score compared to male 1. Now, we could talk a lot further about why this might be, but I'll talk more towards the end on what additional data we're missing in order to make meaningful conclusions out of this. All we can kind of observe right now is that there's something about male 2's vocalizations that is inducing very low clustering scores in relation to accuracy in comparison to the ground truth. And it's also quite interesting that, or kind of surprising rather, that even though we compared these metrics for all conditions of singer, register, and gender, the singer condition was really the only one that, produced any statistically significant differences. Participant information and cluster metrics. So we wanted to analyze how participants perceive vocalizations in relation to the ground truth labels. And we did this by calculating correlations between participant cluster performance metrics and their profile information. Now, profile information is just information individualistic to the participant, such as their level of musicianship, perceptual abilities, how they performed in terms of inconsistency during the task, and how well they understood the task as well. I'll make some more general observations about this table at the end, but it is a video, so you can observe it later as well. Tombold spaces. Finally, we analyze the average dissimilarity ratings between all ground truth classes grouped by condition. We use multidimensional scaling to generate the Tombold maps, which are presented above. But a word of caution, there was quite a bit of intra-class variance, such as breathy to breathy comparisons were higher in females than in males, and the same goes for vibrato. So that's not really so representable in multidimensional scaling, but still the general structures and shapes should hold. Looking at the comparison between registers first, which are the 2 graphs on the left-hand side, we can see that the distances between straight and belt and vibrato, fry and vibrato, are larger than they are in the high register conditions. And similarly, if we look at the comparison of male and female, the 2 graphs on the right-hand side, we can see that for males, the distance between straight and breathy are considerably larger than females, and conversely, fry and vibrato it's a larger distance between those 2 classes for females than males. Overall, we can this shows us the differences between the various conditions and shows us that the perception of Tombold space may not be consistent for everyone at any condition. And one last general observation is that there does seem to be some clustering between the classes of straight, belt, and vibrato, while the fry and breathy classes are much more distant. Should disclaim that it does seem that there would be quite a bit of noise in the data as well. This was hinted to us due to the lack of conclusive optimal k-values generated from sum of squared errors, but also the feedback that we got from participants pointed out some confounding variables when it came to influencing their dissimilarity ratings. And this included performers' lack of control, distortion, temporal pitch variation, total amount of notes per sample, melody, and assumed class types. There's also a bit of quite a bit of variation in vocal set as well, such as the volume of singers, the style of performances changing, so that we can also make some revisions to mitigate that. And finally, our conclusions was overall, we were quite surprised that participant data was not easily separated into clusters beyond 2. And we were expecting them to kind of at least be a little bit closer to the ground truth, which would be 5 labels generating 5 clusters of some sort. Gender and register was not indicative of how robust the cluster structures were going to be, or perceptual agreement with the ground truth, which is quite surprising. Participants with more musicianship relevant to singing were in fact more likely to perceive singing styles similar to the ground truth. And we've been able to show our timbre maps, which show the differences between genders and pitch register as well. In future work, with the participant feedback we've gotten from this study and our observations on clustering behavior, it does give us some useful information if we wanted to make a less noisy data set. There are some steps we can take for that. And the metrics of inconsistency and task comprehension were indicative of accuracy as well. So we can use these metrics to filter our participants if they didn't quite understand the task. And also using acoustic parameters in parallel to the dissimilarity data would be extremely useful for 2 reasons. One, it gives us a lot more interpretation regarding the dimensions in multidimensional in the in the timbral spaces to be able to make meaningful interpretations of what they mean, and especially because we have a lot of dissimilarity information between singers. Acoustic parameters would certainly make it more obvious why those differences exist. And last of all, the timbral maps that we can generate from these dissimilarity matrices can be used as regularization terms in machine learning techniques, or specifically with neural networks, to encourage a latent space that mimics the topology of human perception of the singing voice. That's it from me. Thanks very much for your attention, and I guess I'll be happy to take questions now.
Thank you very much indeed, Brendan. That was a very nice presentation. There are no questions on Slack yet. I've got some questions of my own. And I'm kind of interested in a way in this thing where you talk about the task comprehension. Because when I looked at the task in the paper, the task talks about basically you ask the people to say, you know, which things are similar. So it seemed to me the task is paradoxically, the task is very, very clear, except for the fact that similarity is something that can be very subjective, because just for starters, people can decide to say things are similar on many, many criteria, just because music is so multidimensional. So I wondered whether it really was about task comprehension, or whether it was really about that you'd actually allowed people quite a lot of interpretation. And it seems to me with studies like this, that's always an important choice about how much you guide people. And if you don't give them much guidance, I think in a way, you know, whatever they come up with is then going to be right in a sense, almost what they say is the ground truth rather than the ground truth that you're sort of hoping they'll discover. I mean, I realize that's a bit of a crude way to put it, but can you say something about this interaction between the task comprehension and this notion of, well, what is similarity?
Yes, I found that we did a few pilot studies, and the amount of times I had to rephrase the instruction to the participants was there were a lot of drafts, and really I was trying to go by the philosophy that whatever you're hearing, if you can mentally strip back the slight variations in pitch. We try to keep all the pitches quite similar to each other, but there's always going to be variation when you're doing a random selection. If you can kind of strip that away from your evaluation, as well as the utterance being used, and then through some kind of mental dimensionality reduction, be able to assign a scalar between the two voices, should show us at least how they perceive voices very differently. And I guess this experiment was done with the faith that everyone would do it in a roughly similar way. However, as we've seen from the participant feedback, there were quite a few deviations from interpretation, which gives us a way to reevaluate how we set up the study. There's definitely some obvious choices that I would make, such as only having comparisons between strictly the exact same notes from each singer. It was my kind of hypothesis that slight deviations in pitch or changes in notes weren't really going to affect the timbre perception, but that's just me from a musician's point of view, and it can be very different for a non-musician as well.
I mean, on the other hand, you could argue that if you do too much of this stuff, then what you're left with is it really music? I mean, in the real sort of music tasks that people face are essentially quite noisy situations. I guess there's some tension there.
Yeah, I feel like there must be a sweet spot that we have to very carefully try and articulate. Okay. Yeah, otherwise it all sounds the same.
Okay, got a question from John. You mentioned your interest in electronic music. A lot of vocals there are processed pretty heavily, and the pitch could be changed by an octave or more. How do you think this kind of processing would interact with your findings?
So interestingly, I also had to make this clear in the study as well, that none of the files were actually synthesized or edited in any way. The only thing that we applied to them was normalization, and that was to make the listener's job much easier in terms of comparing two different voices, because there was variance within the data set itself. I've forgotten the second part of that question. Sorry, what was it?
Oh, sorry, I'm juggling, so I've got...
I should have it here.
Yeah, how do you think this kind of processing would interact with your findings?
I think it wouldn't do very well. If you think of someone auto-tuning a voice down an octave, the formants are all kind of out of whack, and it gives them a much deeper, bassier voice, and you imagine like a much bigger person singing a sound that's been pitched down an octave, or a much smaller person if it's been pitched up an octave artificially. So I don't think doing processing on top of these natural voices would be useful for this study.
Okay, thank you very much, Brendan. Nice paper.
Right. Thanks very much, guys.
Thank you, bye. So the next paper is by Tay Bazin, Gatien Hadjer, Philip Esling, Mikkel Malt. I apologize if I've mispronounced names. At a real conference, of course, I would have been able to grab you beforehand and asked. So the title is Spectrogram in Painting for Interactive Generation of Instrument Sounds. So are we ready, guys?
Can you hear me?
Yes, I can hear you. Just going to mute.
Do you have the video? Do you see my screen?
No. Sorry, I'm muted. No, I can't see your screen.
Here I go.
Oh, I can see it now.
Okay. All good?
Good.
Okay, let's get started. So hi, thanks for having our work at the conference. I'm Thais Bazin, and this is joint work with my supervisor at Sony CSL and IRCAM, Gaëtan Hadjer, Philippe Esling, and Michael Malch. As the title states, we're going to be talking about in-painting spectrograms to interactively generate instrument sounds. So first and foremost, let's get into it. What's it all about? So we are proposing an efficient VQ-VAE and transformers-based architecture for in-painting of instrument sounds. I will get in details on all of those terms in the rest of the presentation. This architecture that we propose is trained on the NSynth dataset of instrument sounds, and we also open source an interactive web interface for this model, since we believe that just releasing a model without making it actually usable would not be very beneficial for the music community. So what does it actually do? I will now show you a small video demo of the model and the interface, in which I start by importing and analyzing sample from the validation dataset of NSYNC. Then I will regenerate the beginning of that sound to introduce a more percussive attack. And for that, I will use a pitch with a keyboard and pitch C60. So C4 constraint. And finally, I will generate the low frequencies of the sound to add more depth. And for this, I will use an organ with pitch 24 constraint. The original sound is playing. I select the beginning of the sound, and it's regenerated. Now I change the constraints, instrument and the pitch. I select the bottom frequencies of the sound. And there you have it. The sound has been transformed. So now, the motivations for this work are as follows. First, sound design is a difficult task. It requires expert knowledge. It's often the case that mainstream synthesizers have over 30, if not on the order of 100 parameters, and tuning them to first reach the sound that you want and also perform the modifications where you want them to happen is difficult. So there is also no local control in existing AI systems for sound generation. So systems have been proposed to try and alleviate these difficulties in sound design, but it's difficult as well, since audio data first is very high dimensional. So modeling it using neural networks pretty complicated. And as I'm stating, there is no local control. For example, in the GAN-synth model by Magenta, a very popular model, a single vector is used to constrain a full 4-second sound. So if one wanted to modify just the beginning of the sound, it would not be possible. And on the opposite of the spectrum, so GAN-synth is very sparse conditioning. On the opposite of the spectrum, we have models with very dense conditioning, such as WaveNet, where a full conditioning sequence is required to generate a sound. And those sequences may be sampled, those conditioning sequences may be sampled at a high sampling rate. So our approach tries to solve those problems with the following contributions. First, it is in-painting based, which I will define in the following, meaning that it makes it possible to perform local transformations. Second, it's using a highly downsampled model, which amounts to making it very fast. And finally, it's also possible to use auxiliary label-based conditioning, such as instrument type or pitch, so that it's very flexible and controllable. So now, what is in-painting? So first, generalities on it. it's a modeling scheme where one requires a model to reconstruct parts of missing parts in an input. So it's closely linked to masking, where one will input a mask onto some data and try to reconstruct the missing data. Therefore, the models that do inpainting are required to compute local conditional distributions. And finally, we want to note that those inpainting models are very easily amenable to interactive usage, as can be seen in the following demo video by NVIDIA for image inpainting. Here on the left, the user is inputting a mask on the original image, and the inpainting model is trying to reconstruct the full image by filling in the blanks from the mask. So now inpainting and its applications to music. For now, it has only been done in the symbolic domain. And in that domain, the idea is to regenerate parts of a sheet given the context. Examples of this include the deep bar model for bar choral generation and the anticipation RMN model by Gaëtan HS and collaborators for bidirectional regeneration of symbolic music sequences. And this can be very easily integrated into professional DAWs, as you can see in the demo video now playing. This is an interface that we built at Sony CSL. On the left, you have the interface, which allows to regenerate local portions of a symbolic sequence of music and route the generated symbolic music to Ableton and synchronize it with Ableton to use it in a professional music production environment. This allows to very quickly transform data, and the end benefit is that by performing local regenerations, the users at the end of the process really feel like they have actually created the result, and it's not simple one-button generation. So now, how to perform inpainting on audio? The challenges are as follows. First, there are standard requirements. So we want to have good reconstruction quality, as well as efficiency. It has to be fast for it to be usable in an interactive context. And also, we want the models to be flexible. So we want to have as diverse outputs as possible. And regarding the interaction, we have to define the domain on which to operate. So what will those inpainting operations operate on? And also a scale, since these masks have to be convenient to use. We don't want to ask the user to operate on masks sampled at, say, 48 kilohertz. That would be very inconvenient. And the solutions we propose for this are as follows. We will be working on male spectrograms, since this provides a nice interpretation of the inpainting process as sort of a multiband equalizer. We will be introducing coarse downsampling using the VQVAE model, which will convert sound into very compact discrete sequences. And finally, we will be using transformers for powerful inpainting-based editing. So the approach we propose is as follows. It's resumed in this large graph. Let me try and get the annotations. Yeah. So first, I will be talking about the VQVAE part, which takes an input spectrogram, converts it to discrete code maps, and reconstructs it then to the original spectrogram. Then I will talk about the linearization scheme that takes discrete code grid and converts it to a sequence a flattened sequence so that the transformers can then operate on it and perform in painting. So what is the VQVAE? Generators first. It was introduced by DeepMind, originally for images. It's all in all a standard autoencoding and architecture, meaning that it's trained for reconstruction. But the difference with standard VAEs is that the bottleneck is quantized in those models. So models learn to project the latent representations from the variational autoencoder onto a learned dictionary of code words. And this leads to having multi-scale representations. So here we have the original image, which is consecutively transformed first via an encoder to a smaller downsample version of it, then another even more so downsample version. Then we have the VQ part, which converts it to discrete codes. So it's just then an array of discrete indexes, integer indexes. And we use this top conditioning map to constrain the bottom decoder, which will also quantize the less downsampled latent representation. And finally, we use both of those integer grids to decode back to the original image. So the main idea is that we convert an original large image onto two small-scale integer grids. Now, how do we apply this to spectrograms? We will have 4-second sounds, and we use the MEL-IF representation proposed by Gantin. So it's MEL amplitude and instantaneous frequency. We unroll the phase to make it smoother. And we augment it with phase masking so that we hide portions of the spectrogram where the amplitude of the sound is low, so that the model does not have to focus on modeling those areas where the phase gets very random and not regular. Finally, we use ResNet UNet-like encoder-decoder architecture, so which will map the input spectrogram to the latent representations. And this yields ultimately a bottom grid of 64 times 8 code, discrete integers, and a top conditioning map of 32 times 4 integers. And we train this with an L2 loss. So at the end of it, we have two grids. The first, the smaller one is a very high-level description of the sound. And the larger one, the bottom code map, is a more refined description of the sound, which we can hope represents the timbre of the sound. Then we have to linearize those grids to perform autoaggressive modeling on it. The top one is linearized in a very simple linear fashion, starting from the lower frequencies. So here we have a portion of the sound, the extract, and this code map here is linearized by just going in the order of the smaller frequencies first. And for the bottom code map, we align it with the top code map by going, but we do it using a zigzag-like order. So since here, those two grids represent the same sound, we see that we have more finer sampling here. And those 4 codes here correspond to the single code in the top map. So we will go in this order here to convert those 4 codes to linearize those 4 codes, eventually giving us a linearized representation where sounds that correspond to the same zones in the spectrogram are aligned in the sequence. This compensates for the F-sampling and ensures that the conditioning is aligned. Now, moving on to transformers, some generalities. Those are attention-based models where the model will attend to positions of the inputs. So it can learn to know where to look to provide good answers. It's very powerful for sequence. Yeah. Did I stop or?
Yeah, you can sum up.
All right, okay. So very powerful for sequence-to-sequence modeling, and there are multiple schemes of attention, which I will scheme on. Our spectrogram transformers are described here. We have mask attention in the top transformer so that it can look at all of the top code map when we regenerate it. And the bottom transformer looks at the top code maps and allows to regenerate the sounds locally, conditioned on it. We train autoregressively with label smoothing. We randomly sample masks in the top code map during training, and we use factorized time and frequency positional embeddings so that the models know where to look at. Finally, we can introduce global conditioning via one-hot encoding. Now, a quick note on Jukebox. It's concurrent work from OpenAI with a very similar framework. So it's VQAE and transformers, but we have very different goals. In OpenAI Jukebox, it's a huge model for full song generation, and the quality of production of results is very impressive, but it's very slow to sample and not usable in a musical production context. Whereas our approach is much more compact, so the quality of reconstruction is less impressive, but it's very highly reactive, and it was built with musicians in mind. So now going back to the interactive interface, we think it's crucial for adoption by musicians, and also it's a web interface, it's responsive, and it's so that it's easily deployable and accessible for large audiences. It's open source, and it's using a simple API, so that it's easy for researchers to plug in and adapt to their own models. We provide, it allows novel sound transformations, such as multi-scale transformation, where one regenerates the full top map, which will sound large properties of the sound, but also it's possible to regenerate only the bottom top code map to perform timbre transformations. And this allows to create hybrid sounds through iterated editing. Here I have audio examples that I can show.
Time's up.
Okay. I will just go over to the final slide. It's the same sound, but it's always regenerated with a different timbre by modifying the bottom map with different constraints. You can see that it's sharing a lot of sound properties, but the timbre is different. And now ongoing work, which will allow us to move to maybe the discussion. Okay.
Okay, thank you very much. So we've still got a little bit of time. We haven't got the full 5 minutes for questions. Very good talk. Thank you very much indeed. Interesting work. Now, there's no questions as such, but Bob says there's similar work has been done on something called compressed sensing. Are you familiar with that work?
Well, for audio specifically, not, but I'm very interested in learning applications.
Okay, so afterwards have a look at the Slack and just find out about that.
Sure, thanks.
Bomo says, can you show an example of pitch interpolation or melody in painting on spectrum often interpolates timbre but not pitch? I'm not quite sure I understand the question myself.
Not too sure either. So regarding melody interpolation, we have to build that up. For now, the model only generates individual sounds. So moving on to melodies and with the interface would be is interesting. It has been requested by musicians to be able to really transform a full sample of rendered melody. But for now, it's tricky because the models, actually, the difficult part in that is that the representation for now with NSynth is very aligned to the second zero. So I'm being clear, to really take into account a full melody, we would first, I guess, have to detect onsets and then apply the model on a smaller window localized on that onset. It's tricky. it could be done. It's super
Okay.
interesting. I mean, I want to do it, but for now, we're
Okay,
only at
thanks very
the
much,
single
Tay.
sound level.
Yeah, thank you very much, Tay. Good talk, thanks. Okay, so our last paper is a short paper. This is by, and again, I apologize if I mispronounce these names, but I'll do what I can. This paper is by Manos Plitzis, Cosmos Kritsis, Maximus Kaliakatos, Papakostas, Agelos Krakis, and Vasilis Katsouras. I really apologize for anything I've done to your names there. So are we, and the paper is entitled Towards a Classification and Evaluation of Symbolic Music Encodings for RNN Music Generation. Okay, we're ready to go, guys.
Hello.
Hi.
Let me share my screen. So,
Okay.
that's okay. Okay, good evening. Before I begin, I would like to mention that this work is done. Part of this work was done for my master's thesis that I presented this September. And first, I would like to play you a couple of pieces of computer-generated music. And the second on the bottom. Okay, so these two pieces of music were generated by neural networks, which were trained on symbolic musical data. Both pieces share the first bar, which comes from a human-composed Irish tune, and this gives us a starting seed for the network. The networks were trained on the same musical corpus of Irish folk tunes, the only difference being the form of the data, or its encoding or representation, as it's called. The first example with its repeated first bars kind of hints at an A-B structure, while the second one sort of has many disconnected melodic phrases. Are these perceived differences due to chance, due to some other factor, or are they due to the different encodings that were used to train the network? So this is our main research question. So does the encoding of musical data influence music generation? And which is the best way to systematically study it? To answer this question, we put some limits. We limit our scope to sequential representations of monophonic music, and we study a well-established method, music generation. We want to study the encoding's effect on the generated music, as well as the difference in internal representation, meaning what the network understands. For this purpose, we study three types of encoding, which are all widely used in generation systems. The first one, time step-based encoding, is where each token in the sequence has a predefined time length given by the resolution. It uses three types of tokens. Notes start with a note-on token and rests with a rest token. And held notes are represented by a same as before token, which is added for the duration of the note after a note-on. A problem with fixed time step encodings is that sequence length increases with resolution, so it becomes memory intensive when we want to encode a more expressive music such as a real-time performance. One way to solve this is to move to what we call an event-based encoding, Here we also have note-on events and a separate note-off for each note. But here time is handled by a special advanced time token, which, as its name suggests, advances time forward by a fixed amount. And this puts a lower and upper bound on sequence length, depending on the number of notes. The last encoding we used is a popular text-based encoding, used mainly in the folk music community to transcribe and share melodies. We used a tokenized version instead of feeding the network character by character by grouping characters in musically meaningful tokens. We used a shallow one-layer network, mainly because fewer parameters are easier to visualize and understand. We used a dataset of Irish folk tunes in the ABC format, which was used to train the folk RNN network, of which we kept only the pieces transposed to C and with a 4/4 time signature. So in every step, we tried to keep everything as simple as possible in order to focus on the effects of the encoding. So after re-encoding and processing the original dataset, we already see a major difference in the distribution of our data for its encoding. The time-step-based dataset on the left is heavily skewed towards same as before events, which are depicted in red. Something that gets worse as the resolution gets finer. Not-on events and rests are depicted in blue. Their frequency on the y-axis is on a logarithmic scale. And same as before, events are at bar in red. And they occur roughly 2 orders of magnitude more than all other events. The event-based dataset is also somewhat skewed, with advance time by 1/8 of a quarter, which are seen here. Oh. Advance time tokens are in green. And the advance time by 1/8 tokens are roughly 1 order of magnitude more prevalent than all other tokens. So other than the skewness of its distribution, the sequence length that is needed to encode a phrase also changes between the encodings, which makes them sometimes difficult to compare side by side. First, to compare the musical output of our network, we used the standard musical measures, which are widely used in musicology to analyze symbolic musical scores. We compared 200 generated pieces from each encoding with the original tunes, whose first bar was used as a seed for the pieces. We used statistical methods proposed in the literature. In our case, the approach did not show consistent results because when comparing measures in a macro scale across datasets, it looks like all the networks produced music more or less similar to the original dataset. We decided to first look at the network output and listen and gain some intuition as to where the differences lie. So one observation, which is consistent with the examples at the beginning, was how the ABC output seemed to count consistently better and have more of a long-term structure. To investigate this further, we visualized some of the network parameters while it processed a piece it had not seen before. So on top, we see the network input in ABC format without a header, but with a starting song token. In the middle, we see a visualization of the activations of the 32 LSTM layer neurons, and with yellow being more activated and dark blue less. On the bottom, we have a visualization of the top 5 predictions of the last layer of the network. Oh, sorry, the slides keep going forward. With yellow being again higher probability, dark blue being probability close to 0. Looking at the activations, we see that the network has learned some patterns to recognize bar lines, especially this neuron here on the starting song. And also it can predict bar lines with a very high probability, as seen here, one step before a pattern occurs, which indicates an ability to count consistently. So looking at the other representation, the event-based, we see a different picture. As there are no explicit bar lines in the coding, we have marked each measure in a different color here, with 500 being the starting song token. There's a general block pattern every roughly 3 to 4 tokens, which we can interpret as the network noticing when to start and stop a node, meaning that it has understood the local characteristics of the encoding. So it sees a note on event, so it knows that what follows is an advanced time event and then a note of event. Sorry. It is fairly certain in its predictions for both those tokens, while when predicting a new node, the probability is divided between different node on events, as in here, which allows variation for melodic variation. So the same local behavior is evident in the fixed time step trained network. Here it's also evident by the size of the same as before blocks that the network has learned to mostly output 8 nodes, which is also the most prevalent duration in the dataset. So can we now answer a research question? Our research shows a significant influence of encoding on neural network music generation. But to determine and quantify this influence can be difficult. This is because in a complex music generation system, it is difficult to isolate the encoding's effects, especially if the encoding is vital to the design of the network. Translating data from one encoding to another losslessly is also a problem, either because it is theoretically impossible, or there is no available software that can handle the task consistently. Lastly, evaluating generation systems in general is non-trivial, especially with music that has no universal semantic content. An obvious continuation of our research includes varying the dataset, the models used, the size of the models, but also trying to design new encodings that can be suited to specific tasks. And that's it. Thank you for your attention.
Okay, thank you very much. That was a great presentation. So another good paper. Can you hear me?
Yes.
Else?
Yes, I can hear you.
Great. So we've got one or 2 points on the Slack. So Bob says, why do you use such a shallow network with so few LSTM units? I think in this case, the generation is going to be very poor, no matter the representation. What's your feelings about that?
Yes, the reason for this is that our main concern wasn't to show differences in quality of music generation, but more to study the behavior of different encodings or representations with a type of network that has been used over and over again in music generation. And an added bonus in using a shallow network is that you can visualize everything in a very short, small. I don't know. You can have a good overview of all the parameters.
Okay. So Bob makes another point which you might find interesting. So he says also focusing on transcriptions in 4/4 increases the difficulty of the problem significantly. Try polkas in 2/4. Was that a consideration or?
Yes, the main reason for restricting ourselves to 4/4 is that the nature of the data set, having like a header, the ABC format, makes if you have tunes in different time signatures, this makes it a classification task for the network. So it can make a piece in 4/4 and then another in 3/4. So we decided to limit ourselves to just one time signature, and we chose for fourths because it was the most prevalent and we had the most data.
Okay. Just one thing I wondered was, I mean, what you did some very rigorous work, and then you seemed to do some quite informal listening tests just with the team.
Yes.
I actually think it might have been worthwhile doing formal listening tests where they were blind tests, because it seemed to me you knew certain things that maybe a blind test person might not actually know. Any views on that?
Yes, I think you're right. We simply did not have enough time to do like a formal listening test with all the parameters we wanted.
Okay. There's a little bit of extra comments from Bob, but those might be best looked at offline and maybe have a little discussion. So thank you very much. Thank you very much. That was a nice paper, nice discussion. Thank you to all the presenters. Very interesting set of papers. So that's good. Don't forget the conference is going on later and into the evening. And the next session is very soon. The next session is at 18 hours 15 CEST time. So that's in 25 minutes. I apologize. I know this session is timed to go on for another 10 minutes. I mean, I think it probably should have not actually taken up the whole time, but so I apologize if my sharing has been a little bit lax. But you've still got you've still got 25 minutes to have a coffee or whatever, or a beer before it happens. Actually, we have finished on time because the 15 minutes was actually built in as a buffer, but Bob's just informed me of that. So maybe I'm just too guilt-ridden as an individual. So yeah, I mean, there were a few technical issues swapping between, and just doing it this way does need that buffer. So yeah, I really appreciate having the buffer. Okay, so thank you very much to everybody, and see you later, and see you in about 25 minutes at the session by CJ Carr, which as I say is starting very